Welcome to section 10.1. Here we are beginning our journey through multivariable calculus. That journey is going to take us predominantly through the third dimension. So a lot of the work we're going to be doing is in 3D. So we need to start off the course naturally talking about the three-dimensional coordinate systems. So we're used to dealing with finding a point in a plane using two coordinates. So we're used to the point x, y. But in order to locate a point in space, we need to use three coordinates. So we're still going to have the x coordinate and the y coordinate, but now we will also have a z coordinate. Along with this third coordinate z comes an additional coordinate axis. So we're going to have three coordinate axes, x, y, and z, which are all going to be perpendicular to each other. So again, as a point of comparison, we have the xy plane here. So the x-axis, the y-axis. If we want to find a point, just something arbitrary, we find the x value, we find the y value, and that's our point x comma y located in the plane. If we want to identify a point in space, we're going to have now the x-axis and the y-axis down here, and the z-axis giving us that 3D component. So everything before was on this flat surface. Now we're bringing things up into the third dimension. So if we want to find a point, we can still do it very similarly. So we find the x coordinate, we find the y coordinate, but now we also have a z coordinate to take into account as well. So it's going to be moving up. Now, we'll look more in a little while about the plotting of points in 3D, but essentially what we're going to do is we're trying to get to some point up in here that has this height. So we're going to go ahead and just create the sides of a box. This is a technique we have for visualizing a point in 3D. So you can see right there, that point is going to be the point in question. That's the point XYZ. If we looked at the point that corresponded, like this point XY that we had over here, in this new set of coordinates, this would be the point XY0, because Z would be 0 when we're down here dealing with the XY plane. Now, like I said, all of the coordinate axes are perpendicular to each other, so we know, right, that the XY axes form a right angle with each other. Well, X and Z also form a right angle, and Y and Z also form a right angle. So they all have that same relationship to each other. Now, when we're looking at this graph and saying, okay, well, X went this way, Y went this way, Z went this way, who's to say that they have to go that way? Well, in order to determine the direction that the axes point, we need to use what is called the right-hand rule. We call this the right-hand rule because it can be done on our right hands, establishing the direction of the X and Y axes, and it's then giving us the direction of the positive Z axis. So if we take our pointer fingers, and you can do this on your hand right now, but take your right hand and use your pointer finger and point it straight forward, and then try to form kind of like a 90-degree angle here with your middle finger. Point it inward towards the side of your palm. So now you've created this shape with your fingers, and now stick your thumb up. Whatever direction your thumb is pointing, that's the direction of the positive z-axis. So if you go back and look at the one that we just did, if your pointer is going this way and your middle finger is going this way, your thumb would be pointed this way. Okay, because these axes also do go into the negatives, right? The negative x's are all back here, negative y's are here, and negative z's are down here. But in terms of positive direction of the axes, this is how we can make that determination fairly quickly. Now, since we have 3 axes, that's also going to create multiple coordinate planes for us to look at. So the 3 coordinate axes determine the 3 coordinate planes. I have those pictured here. We're used to working with the XY plane. So that's the one where we've spent all of our time in algebra and calculus and all of that stuff. We've been living here in the XY plane. Now the XY plane is basically just like a flat table where we can do some work, but now that we're in 3D, we also have the XZ plane over here. This is the plane formed by the x-axis and the z-axis, and the YZ plane, which is formed by the y-axis and the z-axis. As you can see, I've created kind of these dotted sections here. These planes do extend in all directions, so it's not just the front section here. They do extend onward further into the positives and the negatives in all directions. But these are the coordinate planes. So the XY plane where z is 0, the XZ plane where y is 0, and the YZ plane where x is 0. Now, if we want to plot points, we of course use that ordered triple, that x, y, z. Having 3 axes means that we can have 3 intercepts. So we can establish an x-intercept, a y-intercept, and a z-intercept. The x-intercept is whatever point we're looking for along the x-axis, right there. So it would have a coordinate of x, 0, 0. If we're looking for some point along the y-axis, that's the y-intercept. That's 0, y, 0. And the z-intercept would have a coordinate 0, 0, z. Now, when it comes to plotting points that are not on the axes, let's get a little bit of practice in with this. So we can use a method similar to what I showed up above, where we draw a rectangular box to help us out. This is particularly useful because in 3D, there is an extra layer of uncertainty involved in point plotting. If I plot a point right here, for example, that does not give a clear picture as to where that point is supposed to be. That point could be somewhere like way up here, or like more like this, like way up here, like in front of this set of planes. Or it could be way in the back here, down back behind the planes, the coordinate planes, or anywhere in between. So the perspective is shifted a little bit. So let's take a look at this first point here. So we're looking, so x, y, z. The x coordinate is -4. So we're going to go not positive x, but negative. So 1, 2, 3, 4. So the y is going to be +3. So they're going to go 1, 2, 3. and z is -5. So 1, 2, 3, 4, 5. And now we need to create the box. So we go the x coordinate and the y coordinate, we connect those. Those are going to be one side of the box. We can connect the y and the z as best we can. And this is not an art class, so you don't have to be too worried about making it look pretty. As long as it's in the right vicinity over here, you should be fine. And then we'll complete this side of the box right there. And the point that we're looking for is going to be down here. It's the furthest away from the origin on the box. So we have the whole box here. As you can see, whatever point over here is furthest away from the origin, that's the point in question. So this is the point -4, 3, -5. And again, it's this point because this is the point that has an x coordinate of -4, a y coordinate of 3, and a z coordinate of -5 to get us down there. If we take a look at part B here, 3, -2, -6. So we're going to go 1, 2, 3 in the x, -2 in the y, and -6 in the z. So that's going to be down there. So we'll connect those. And connect those. And there's our point right there. So that's 3, -2, -6. And again, we look, that's 3 in the x direction, -2 in the y direction, and -6 in the z direction. Gets us down to that point. And the nice thing about point plotting and practicing this, if you're not entirely comfortable with this yet, is you can just make up your own points. Try making up some points that involve like maybe all positives, all negatives, some mix of the two, to try to get more comfortable with visualizing where these points exist in 3D. Now, in addition to working with points in space in 3D, we can also work with surfaces in 3D. So we're used to dealing with R2, that describes the set of all ordered pairs that are two-dimensional. Similarly, R3 is the set of all ordered triples of real numbers. This is called a three-dimensional rectangular coordinate system. So rectangular, right, like these shapes that we're drawing up here. We can use this system to sketch surfaces in R3. So if we take a look at some examples here. So what surfaces in R3 are represented by the following equations? So we have z equals 3. So this value of z equals 3, we know that that's going to have a height that's right here. So height of 3 on the z-axis. But the question becomes, is it just like this point right here? Because x and y are not mentioned. Now, since x and y are not mentioned, that actually means that they are unrestricted. It means that we do not have any specifics that we are requiring for x or y. They can be anything. So make a note of that. So note x and y are not specified. So they can be anything. So that means that we could have x be 0 and y be 0. That would be right here. We could have x be 1 and y be 0. We could have x be 2, x be 3. We could have y be 1 and x be 0, y be 2, y be 3, be 4, etc. We could have some combination of those points. You could have them go into the negatives back here. You can have them go anywhere you like. And ultimately what that's doing is it's creating something that I think I can draw. Close enough. It's creating a plane. So this plane is all the points that have a height of 3. So all these points. So this is a plane through z equals 3. So it's a completely flat surface. It's parallel to the xy plane. So kind of like if you just had like a piece of cardboard or a piece of paper just laying flat 3 units above this table or the ground. Okay, and x and y take on R2. They can take on any ordered pair that we want. So again, you can have, the point 1, 1, 3, the point 5, 7, 3, the point -2, -17, 3. X and Y can be any ordered pair that we want, and then the Z component will be 3, always. For part B, we have a similar situation, but here Y equals 5. So we're going to go 1, 2, 3, 4, 5. Once again, y is specified at 5. X and z are not. So x and z could be potentially anything, right? So you could have them both be 0. You could have x be 1, 2, 3, 4, 5, etc., or negatives. Z could be positives or negatives. And ultimately, it's tracing out, again, a plane. And I visualize these planes with rectangles, but they do extend out in all these directions infinitely. So this is just so that we can visualize at least a piece of it. So, but this is going to be a plane through y equals 5, and x and z take on R2. And lastly, if we have y equals x. So now something a little bit different here. Here we have 2 variables getting involved. Now, if this equation was given to us in 2D, we could figure out what this equation is. This is the equation of a line, right? The line y equals x. If you think y equals mx plus b, this is a line with a slope of 1 and a y-intercept of 0, right? It's really just diagonal. So it goes diagonally, it cuts through the xy plane like that. Now, because z is not specified here, this is not just a line, it is this line, but z here, specifically on this part of the line, that's z equals 0. But you could also have the line up at z equals 1, at z equals 2, z equals 3, z equals 4. You could have it negative 1, negative 2, negative 3, negative 4. It could just keep going and going and going. And ultimately, it does also create a plane. So this plane is coming out. It's kind of like coming out of the page at us at a diagonal angle here. So this is coming straight out, and again, it goes up and down. It does go back as well, and it comes out forward also. So, but even expressions that we had in 2D that meant one thing, in this case, a line in 2D, could be represented using 3D surfaces when you bring in the third coordinate, when you bring in ordered triples. Okay, so this is the plane through y equals x, and z takes on just r, not r2, because z is just one value, one variable. Now, when it comes to working with these objects more algebraically, we can apply a lot of formulas and techniques that we used in algebra to 3D as well. For example, the distance formula. The distance formula gives us the distance between any 2 points. Up until this point, it had been between 2 points on the xy plane, but now we can find the distance between any 2 points in space. And the way we do that, so we take this notation with what looks like absolute value. That's the symbol for distance or length or magnitude. This formula will be the square root of x2 minus x1 squared plus y2 minus y1 squared. And if we stopped here, this would be the distance formula from algebra. That's the formula we learn how to find the distance between 2 points in the plane. However, it's also plus z2 minus z1 squared. And this is the distance formula in 3D. So a lot of times you'll find throughout this course that when we do things in 3D, really we're just doing the same thing that we did in 2D plus a z. Okay, a lot of what we do in here is the same as 2D, but plus a z. So if we want to find the distance, for example, between these 2 points, P and Q, so we find the length of PQ, that's going to be 1 minus 2 squared plus negative 3 minus negative 1 squared plus 5 minus 7 squared. So this is negative 1 squared is 1. This is negative 3 plus 1, so negative 2 squared is 4. And negative 2 squared is 4. 1 plus 4 is 9. Square root of 9 is 3. So the distance between these 2 points is 3 units. We can also work with other types of surfaces that are not all just straight lines and planes, which are flat. We can also work with spheres. So we're stepping it up from 2D circles, looking at 3D spheres. Consider a sphere that has center at the point HKL and a radius of r. The sphere is the set of all points P, where x, y, and z, whose distance from C is r. So their distance from the center is the radius. That's how we define a sphere. It's also how we define a circle in 2D. So for the equation of the sphere, it is derived from the distance formula. So an equation of a sphere with center HKL and radius r is x minus h squared plus y minus k squared plus z minus l squared equals r squared. Now, a lot of times we're going to be working with spheres and with objects that are centered around the origin. If the center of the sphere is the origin, then that means that this point HKL is actually 0, 0, 0. So you would get the equation x squared plus y squared plus z squared equals r squared. That's kind of more of our standard form when we have something that's centered around the origin, gives us a nice simpler formula. That's like why we like to work there. Now, when it comes to identifying the equation of a sphere, it's not always given to us in this very nice condensed form here. We have to be able to identify it given other forms. So, for example, show that this equation is the equation of a sphere. Find its center and radius. So what we need to do here, we need to try to get it into a form that looks like this one. So we're going to need to try to get the x's together, the y's together, the z's together, and come up with perfect squares for those expressions. So let's see what we've got here. So I've got x's here, I've got y's here, and I've got z's here. And everything else we'll just send over to the other side so that 6 can go over to the other side. So let's regroup. So we've got x squared plus 4x. We've got y squared minus 6y. We've got z squared plus 2z. And we've got negative 6 over there. Now we need to somehow turn these into perfect squares. The way that we can do that is using a technique from algebra, and that is to complete the square. If you don't remember how to do that from algebra, basically if you have x squared plus ax here, or bx, you're going to take half of this coefficient and then square that number, and that gets added to the end of the term. So this first one, so we're going to have x squared plus 4x. We're going to take half of the 4, which is 2, and square it, and that's 4. For this one, we're going to take half of negative 6, which is negative 3, and square it. So 3 squared is 9. For this one, we have 2. Half of that is 1. 1 squared is 1. Now, you can't just go in and start adding numbers to stuff in an equation. You have to make sure that it's balanced. So whatever we did to one side, we have to do to the other. So we added a 4, we added a 9, and we added a 1. So we're going to do that to both sides. And the whole point of completing the square is that now all of these are factorable. They're all able to be factored very nicely. This one factors to x plus 2 squared. This one factors to y minus 3 squared. This one factors to z plus 1 squared. And on the right-hand side, if you add all these numbers up, we get 8. And this is the equation of a sphere. Right? This is that general form that we established on the previous page. The only other thing we need to look at are the center and the radius. Well, for the radius, this side is going to be r squared. So that means that r is going to be the square root of 8, or 2 root 2, if you like to simplify. And the center, we have to be a little careful, because remember, the original formula was x minus h, y minus k, and z minus l. So when it has a minus already, that matches. So we know that k is 3. However, with one like this is plus 2, which means that in order for it to be a minus h, that's actually the same thing as minus negative 2. Like that, right? Minus negative 2 is the same thing as plus 2, and that matches. So that means h has to be negative 2. Same thing with this one. Instead of plus 1, it's minus negative 1 for L. So the center is going to be negative 2, 3, negative 1. So that's the equation of that given sphere. Now, in that same kind of vein of visualization here, what region in R3 is represented by the following inequalities? So if we look at this expression here, this is that spherical equation, right? That spherical expression. But what we have is it's being bounded in between two values. So if we were to consider this in terms of the equality, if we had x squared plus y squared plus z squared equals 1, this would be a sphere centered at the origin of radius 1. And this one would be x squared plus y squared plus z squared equals 4. This is a sphere also centered at the origin of radius 2. Right, because 2 squared gives us the 4. And these are forming boundaries. So it is greater than or equal to this sphere, and it's less than or equal to this one. So it's everything between those two spheres. So it is the portion of a surface between spheres centered at the origin of radius 1 and 2. And then there's this bit of information right here. Z is less than or equal to 0. So remember, Z tells us how far up and down we're going. It kind of provides that 3D component. So the fact that Z is less than or equal to 0 tells us we only want the portion that's below the xy plane. Right? This is below the xy plane. So we only want the portion of a surface between the spheres centered at the origin of radius 1 and 2 and below the xy plane. Essentially what this part is telling us here is that we only want the bottom half of this surface. So like if we were going to visualize this, there's x, y, and z. So the sphere of like radius 1 would be like right here. The sphere of radius 2 would be out here. We would want everything in between these two, but only down here in the bottom half. Let me draw that a little more nicely. So we're going to have sphere of radius 1, sphere of radius 2, kind of shade that in there, here. And then it's kind of just open in here. So it's like you had a ball, right, that had another smaller ball inside of it, and you just kind of sliced right through them, right below the XY plane there, right? So that's a length of 1. This is a length of 2 all the way around. So this object here, this is basically what this scenario is describing up here. All right. And that brings us to the end of section 10.1. That is our introduction into the third dimension. We're going to be working with it all semester in this class. And we're going to work with more points, with curves, with surfaces, all that kind of stuff. And so we will continue on with more from vector calculus, multivariate calculus, when we come back in section 10.2.